We are asked to find the values of a and b that make this piecewise function both continuous and differentiable at x equals 3. So let's talk about what it means for a function to be continuous. We know intuitively that a continuous function can be drawn without ever lifting your pen off the paper. So something like this would be a continuous function intuitively. But what does it mean algebraically? How do we prove this using math? Well, we find a point and we ask ourselves if it is continuous at that point, let's call that point C, three things are going to occur. Number one, the value of the function exists so that there is an f of c right here. Next, we're going to determine that the limit exists at that point. So for the limit to exist at this or any point, then the value approaching point C from the right has to match the limit as we approach from the left. So that is the three-step criteria. Number one, that f of c exists. Number two, that the limit exists, which means that the right side has to equal the left side by definition, because if that were not true, the limit would not exist. And the third criteria is that the limit and the f of c are the same. Let's go ahead and do the three-step test for continuity. First, we're going to do f of 3. We're going to make sure it exists. We have to choose the top expression or the lower expression, and since we're going to be at f equals 3, since that's our c value that we just spoke about, we're going to use the lower expression. So f of 3 means everywhere we see an x, we're going to put a 3, and we're going to determine that that's going to be 9. Next, we're going to do the limit as x approaches 3, both from the left and from the right, and we're going to make sure that the limit exists. First, from the left, since x would be less than 3, we're going to use the top expression. So everywhere we see an x, we're going to put a 3, and we are able to do that. There's no constraints here. So let's go ahead and put x as 3, and that will leave us with 3a plus b. Now, the limit as x approaches 3 from the right is the same thing as f of 3. We're going to use this lower expression, x squared, and we're going to plug 3 into that expression, which means the limit as x approaches 3 from the right is going to be the same as f of 3. Now, in order for us to find the a and the b, in order for this to be a continuous function, this value has to equal that value has to equal that value. That allows us in part 1 here, looking at the continuity, to set 3a plus b equal to 9. Now that we have one equation, 3a plus b equals 9, let's now move to the discussion as to what values would make this differentiable. Now, we have a graph here, and we know this graph is continuous. The question is it differentiable? Now, whenever you see the word differentiable, I want you to think about the word slope. So the question is there a slope at that point? Well, if you look at the left, you have that slope. If you look to the right, you have that slope. We can easily draw one tangent line at that point. That means this graph is going to be differentiable. And not only that, of note is that the slope to the left of the point is going to be the same as the slope on the right of the point. Now, let's compare and contrast that to this graph. Here, we have a graph that we also would agree it's continuous. If we took f of c, we would get this value right here. If we took the limit as x approaches c from the right, we would get that value. If we did the limit from the left, we would get that value. This graph passes all three steps for continuity. But now, as we move to the question of differentiability, look at the slopes. Does the slope exist at point C? The answer is no, because if you're on the left, that is a negative slope. Call that, let's say, negative 10. If you're to the right, that's a positive slope. Let's call that positive 10. If the slopes disagree on either side of that cusp, that means there is no slope. And if there's no slope, there can't be a derivative. So we're going to use that fact. What we're going to do is we're going to take the derivative of the top expression and the bottom expression and set them equal to each other, because that's what has to happen if the graph is differentiable at that point. As promised, we're going to take the derivatives and set them equal to one another. Here's the derivative of the top expression with respect to x. If we do the power rule here, the 1 is going to come out in front, and we're going to get 1a, the b goes away. And here we're going to do the power rule again, and we have 2x. Now don't forget, folks, we're focusing when x equals 3. That allows us to plug in x equals 3 here, and if we have a equals 2x, and we plug in x equals 3, we know that a equals 6. If a equals 6, we can get b. So we're going to go ahead and just substitute here. So we're going to get 3 times 6 is 18. 18 plus b equals 9. Therefore, the b value equals negative 9. So it is these two values for a and b that do two things. One, they assure us that we have continuity. It assures us that the f of 3 equals the limit as we approach 3 from both sides. And secondly, these values assure us that the derivative is going to be the same at x equals 3. The slope is going to be the same at x equals 3. That tells us that this graph is differentiable. If we move to Desmos and we analyze the problem we just did, I went ahead and plugged in, recall this was y equals ax plus b. Our a value was 6 and our b value was negative 9. And then the other graph was y equals x squared for x is greater than or equal to 3. Now, folks, notice this. On Desmos, if you don't put a comma between the function and the restrictions on x, and you use this curly bracket is located right next to the letter P as in Papa on your computer keyboard. On Desmos, you can't find it. And if you put the constraints on x, it'll limit the graph to these regions, which makes an analysis like this much easier. So here we have when x is less than 3, here's our linear graph in red, y equals 6x minus 9. You could see the y-intercept is at negative 9. And then here, when you are at 3 or to the right of 3, y equals x squared takes over. That's this quadratic. And what I want you to notice at the point 3 comma 9, because f of 3 would render 9 on both functions, I want you to look at the slope on either side of that point 3 comma 9. It's the same. That's why it's differentiable. Even if this is a linear function and that's a quadratic function, if you take the derivative and you plug in x equals 3, you are going to get a derivative of 6 here on the quadratic function. That's a slope of positive 6 here. And if we take the derivative here, you of course are going to get 6. Because it's a linear function, the slope of that line is always going to be 6. So the slope to the left of the point 3 comma 9 is positive 6, and the slope to the right of that point 3 comma 9 is positive 6. If the slope is the same, that means the derivative is the same. That means it is differentiable at that point. Before we move to the next example, let's review some other graphs that are not differentiable, even though they're continuous. We already reviewed this one on the upper left. That's called a cusp. Again, the slope is different on either side of that c value. Here, this looks like an absolute value function that's been shifted to the right. Again, on either side of that point, you have different slopes. Here is a continuous function. This is y equals x to the 1/3 power. And what's notable here, folks, is what is happening when x equals 0. This is actually a vertical component to this graph. You could see it better on Desmos. Let me show it to you here. Here, this is a blown up version. You could see at x equals 0, Look at the slope. Look at the tangent line. It's vertical. And we know the slope of a vertical line is undefined. So that's why you're going to see that these types of graphs with a vertical tangent line at a given x value are not going to be differentiable. And it has to do with the fact that when you take the derivative of a function like this, where you have a fractional exponent that's less than 1, and you go ahead and you perform the power rule. Okay, let's go ahead and do that. So here, if we're going to take the derivative of this, y prime would be 1/3 x to the minus 2/3 power. And then this x to the minus 2/3 power is going to go into the denominator. And when you plug in x equals 0, if this is y prime, at x equals 0, this is undefined. So that vertical tangent line will manifest in that x being in the denominator, and when you plug in 0, this will be undefined. Therefore, this is not differentiable. Next, we are presented with this piecewise function where we have this expression x squared plus 2b when x is less than or equal to -1, and this alternative expression ax plus b when x is greater than -1, and we are asked to find a and b that would make this function continuous and differentiable everywhere. So folks, clearly the critical point is going to be -1. Because if you look at this graph here, this is when x is less than or equal to -1. We're going to have a quadratic function. This is going to be x squared plus some constant. And here, when you have ax plus b, this is a line shown here. So this line is going to be continuous and differentiable everywhere. This quadratic is going to be continuous and differentiable everywhere. So the question is, what happens when the juxtaposition at x equals -1? So right there. So that's what we're going to examine, is that point right there. First, let's look at continuity at x equals -1. Okay, in order for the function to be continuous at x equals -1, three things have to happen. First, f of -1 has to exist. We're going to find that in a moment. And second, that the limit as x approaches -1 from both the negative side and the positive side have to exist. And finally, all three of these values have to agree. So let's go ahead and do f of -1 first. If we're going to use f of -1, then we have to use this upper function, this upper expression. So everywhere we see an x in this expression, we're going to replace it with -1. So that means we're going to have -1 squared plus 2b, and therefore f of -1 is going to turn out to be 1 plus 2b. Okay, now let's go ahead and look at the limit as x approaches -1 from the negative side. Folks, that's going to be the same exact thing that we just did. If we're approaching -1 from the left, that means that's the location, the domain where x is less than -1. We're going to use this same function. We're going to go ahead and plug -1, and we're going to get this value here. Okay, finally, we're going to look at the limit as x approaches -1 from the right. Here, we're going to look at this domain when x is greater than -1. So we're going to ask ourselves, what is the limit as x approaches -1 for this expression, ax plus b? Wherever we see an x, we're going to plug in -1 as long as it's legal. And here it is. There's no 0 in the denominator or a negative under a radical. So we're going to end up with that the limit as x approaches -1 from the right is going to be a times -1 plus b, otherwise known as -a plus b. Okay, so now folks, we have to recognize that these three values have to be equal to each other in order for it to be continuous at x equals -1. f of negative 1 and the limit as x approaches negative 1. So what it comes down to, since these are repetitive, is the following: that 1 plus 2b has to be equal to negative a plus b. Now we can go ahead and simplify that in many ways. For example, we could say that a is going to equal negative b minus 1, or we could say that b is going to equal negative a minus 1. All I did here was solve for a. I brought the a to the right side. I brought that negative a to the left side. It became positive a. I brought this 2b to the right side. Negative 2b and positive b gives us negative b. And I brought the 1 to the right to make that a negative 1. When I solved for b, I went ahead and brought this b to the left. 2b minus b is positive b. I brought that positive 1 to the right, and we get negative a minus 1. So we're going to use one of these equations as our first equation to solve for a and b. Next, we're going to look at the derivative to help us solve for a and b. Now, the whole key, folks, is if a function is differentiable, that means we have a smooth total function. So when these two piecewise functions join at x equals negative 1, that's our critical point. It means that the derivative on either side of negative 1 is the same, meaning the slope of the tangent line right here to the right of negative 1 matches the slope of the tangent line here to the left of negative 1. So our goal is to find values of a and b that create these two graphs. Whatever a and b is going to use to create that graph, we got to find it. And that same a and b has to create this graph, where that slope, the derivative of the tangent line on that side of the point, matches the left side of negative 1. So how do we do that? Well, we take the derivative of each of the piecewise functions. So here's negative 1. Here we're to the left of negative 1. When we are to the left of negative 1, when x is less than or equal to negative 1, we're going to be looking at this expression. So we're going to take the derivative of that expression and we're going to get 2x. Folks, notice that the derivative of 2b is a constant. 2b is a constant. If b is 3, that's 6. So we're going to end up with 2x plus 0. So the derivative here is 2x. When we take the derivative here, the x and the b drop out, and all we have is a. So if we find the slope of the tangent line to the left of x equals negative 1, we have to do f prime of negative 1, which means we plug in negative 1 wherever we see an x, and we get that f prime of negative 1 is going to be negative 2. Here on the right, there is no place to plug in x equals negative 1. So that means, by definition, in order for these to be equal, our a value has to be the same as it is on the left side of negative 1, namely negative 2. So by definition, we have figured out that our a value is negative 2. Now, armed with that information, we can go up to one of these two expressions and get our b value. Let's go ahead and use the bottom one. So b is going to equal the opposite of a. So the opposite of negative 2 minus 1, it's going to equal positive 2 minus 1. Our b value is going to be positive 1. So now, folks, we have the a and the b value that gives us this situation: continuous and differentiable at negative 1. Okay, before we finish this video, I can't resist going to Desmos to show this graphically. Here, when x is less than or equal to negative 1, we have the graph y equals x squared plus 2b. We already determined that our b value is 1, so our graph is y equals x squared plus 2. That is shown here. Here to the right of x equals negative 1, namely when x is greater than negative 1, we have the following function, y equals negative 2x plus 1. That's because we determined that a was negative 2 and b was positive 1. So folks, look at what's going on here. Here are the two graphs joined together at x equals negative 1 right here. If you look to the left, that slope is the same as the slope to the right. For both of these situations, when x equals negative 1, the slope is going to be negative 2. That means not only is this graph continuous, but it's differentiable. The slope on that side of negative 2 matches the slope on the left. I'm sorry, let me rephrase that. The slope on the right side of x equals negative 1 matches the slope on the left side of x equals negative 1, and in both scenarios the slope is negative 2.